Now I want to go through the rules for naming ionic compounds. These are compounds that are composed of positively charged and negatively charged particles. An ion, this is the root word of the name ionic compound. An ion is a charged particle. And I have here, if you're on a big screen device, you can see this clearly. If you're not, you won't be able to see this very well. But what we have here is a periodic table with just particular elements that would be really good for you to memorize. And it not only shows their name and the symbol, but it also shows the charges on the ions they make if they make ions. And so you can see group 1 metals all make a +1 charge. Group 2 metals make a +2 charge when they make an ion. And you can see chromium, manganese, and iron and cobalt all make 2+ and 3+ charged ions, whereas nickel mostly only makes a 2+ ion. And copper makes 1+ and a 2+, silver makes 1+, and so forth. You can see there's this staircase here which divides the metals from the nonmetals, and over on the nonmetal side you can see that they're all negative ions that are made, if anything. How can I determine from the formula whether it is an ionic compound or not? This is a really big question because when you look at a compound, sometimes it's not readily apparent if you're not thinking about this rule, whether you should use the naming system for ionic compounds, for covalent compounds, or for organic compounds, or whether it's an acid or not. Well, ionic compounds usually consist of metals together with nonmetals, so we will reiterate. Everything below and to the left of this staircase on the periodic table is a metal. Everything above and to the right is a nonmetal. We're not going to quibble over, metalloids that run along the edge there. So here's the first rule concerning ionic naming. You name the cation first. The cation is the positively charged ion. The T in cation should remind you of a plus sign. Please don't pronounce this word cation unless you're from Louisiana. Cation, the T reminds you of a plus, reminding you that it's a positively charged ion. That's what goes first in the name. That's what's written first in the formula, is the cation, the positively charged ion. If the positively charged ion, and these are almost always, with very few exceptions, they're almost always metals. If it is a transition metal, then you have to provide in the name a Roman numeral for its oxidation state or its charge. And so examples would be copper 2+, copper 1+, nickel 2+, the very rare nickel 4+, if there were such a thing. And then there are exceptions to this rule that you have to use a Roman numeral. There are some things that don't need a Roman numeral to indicate their oxidation state or their charge. Group 1 and Group 2 metals don't need to, because every time it's a Group 1 metal, if it's formed an ion, it should have a +1 charge, like sodium +1, potassium +1. Every time it's a Group 2 metal, if it's formed an ion, it should have a +2 charge, like magnesium 2+, calcium 2+, strontium 2+. So I invoke the Geico moment here. Group 1 and Group 2 metals, always, we know their charge, so it's like, everybody knows that. That's the Geico moment, right? Everybody knows that. So you don't have to write the Roman numeral on a Group 1 or Group 2 metal. And you also don't have to write the Roman numeral on aluminum, silver, or zinc. Aluminum will always have a +3 charge when it's made an ion. Silver, a +1 charge when it's made an ion. Zinc, a +2 charge when it has made an ion. And so those you don't have to, you shouldn't write the Roman numeral in the name. So going back to the periodic table, Group 1 metals are in this first column. Technically, hydrogen behaves like a nonmetal most of the time, but everything below it, lithium and all that below there, behave as Group 1 metals, and if they make ions, it's +1 charged. Next is the Group 2 or alkaline earth metals, and that's the second column. And when they make a charged particle, an ion, it's going to have a +2 charge. Now, next is the transition metals from this border over here, basically all the way over to the staircase. We'll treat them as transition metals, even though some people make a distinction between these that are from this line down and over to the staircase. They still follow the same rules. You have to put a Roman numeral because there's a possibility of more than one ionization state or charge. And also these lanthanide and actinide series metals, they will often, they'll follow the same rule. They'll have a possible several possible charge states, so you might have to put the Roman numeral there. Okay, I just want to highlight again, silver always has a +1, zinc always has a +2, aluminum always has a +3, so you can just write silver and no Roman numeral, zinc and no Roman numeral, aluminum and no Roman numeral, because everybody knows silver is +1, zinc's +2, aluminum's +1. I did put the nickel here. You usually put the Roman numeral 2 there on the nickel, but I do want to point out it's an interesting thing that we have silver here with the +1, zinc with the +2, nickel with the +2, up. And so up and to the right of +2, up and to the left of +2, and straight up you have copper, which can make a +1 or a +2. But again, easy as 1, 2, 3. Silver is 1, zinc is 2, aluminum's 3. And you don't have to write the Roman numerals for those again. Now, second rule in our ionic compound naming rules is to name the anion, which is the negatively charged ion, second or last. So we always name the cation, the positively charged ion, first. That was rule number 1. And we also write the formula with the cation first. And then we name the anion, or the negatively charged ion, second. And we also in the formula write it second after we write it after the cation. So if it is in the ion form, if the anion is the ion form of a single element, then we take that element's name and put an IDE ending on it. And we use the octet rule to figure out its charge if we need to know the charge. So here we have nitrogen, which according to the octet rule needs 3 electrons, so it becomes -3 charged when it makes an ion. And that would be nitride ion. This would be oxide ion. This would be fluoride ion. Even though that was nitrogen, oxygen, and fluorine, this is nitride, oxide, fluoride ion. This is phosphide ion, sulfide ion, chloride ion. You can see we're putting the "ide" ending on there. If the negatively charged ion, the anion that's part of this ionic compound, is a polyatomic ion, you'll need to identify it and know its name by memorizing. There is no substitute for knowing your polyatomic ions by memory, and you'll need to know at least the ones that are on this screen here. If you're watching on a large screen, you might be able to see this abbreviated list of polyatomic ions and some nice information here about when you substitute a sulfur for an oxygen, you put a thio to represent the extra sulfur, or where the sulfur replaced the oxygen. The thio represents replacing oxygen with the sulfur. And here's a nice little note about how when you go down a group, if you're talking about oxo ions, where there's a certain number of oxygens with the element in question, if we're talking about the same group, they all have the same charge. And the names are very similar, right? Chlorate, bromate, iodate. Over here, they all have a -2, sulfate, selenate, tellurate. Over here, -3 for both of them, phosphate, arsenate. So good to see patterns so it can help you memorize. I have to talk about, wherever we have rules, we have to talk about exceptions. Here's a weird exception. Mercury, it's strange. Whenever it shows up, it always has a +2 charge if it's an ion, but here's what I mean. It can show up as an individual atom with a +2 charge, and that's going to be mercury Roman numeral 2, mercury 2. But mercury 1 doesn't show up as a single atom with a +1 charge. It shows up as a pair of them that together have a +2 charge. So you can see that if there's +2 charge across 2 ions, that they must each individually be 1 for their positive charge. But mercury 1, again, doesn't show up. It strangely does not ever show up as just Hg+1. It's always a pair of them with a +2 charge. So how can we determine the ratio of positive particles to negative particles? Well, all solids, liquids, and gases must be electrically neutral. That means the overall charge on a properly written ionic compound should be 0. If the overall charge is 0, then the total positive charges must cancel the total negative charges. And that's our rule for figuring out the ratio of positive ions to negative ions. Here we have Na2S. How to write the name? Well, we have a sodium. Na is the element sodium, written just the way it would be off the periodic table. But sulfur here is an ion form. And for the anion form, we put the IDE ending. So this is sulfide, sodium sulfide. That's all there is to this name. because group 1 metals are always +1 charged, and so we didn't have to put a Roman numeral in there. Just to figure this out, look, sulfide, there was one of them and it had a -2 charge, so the total negative charge was -2. But the sodiums, there were 2 of them because each one of them had a +1 charge, and it took 2 of them to make a +2 charge to cancel the -2 from the sulfide to get us a total overall charge of 0. Okay, here we got a slightly tougher case. We have iron, and you should know your polyatomic ions, so you should know that NO3 -1 is nitrate. So actually that's going to be the clue to tell us what version of iron we have here. If nitrate has a -1 and they're charged, and there are 2 of them, so we've got -2 for the negative side, we must have +2 for the positive side, so it must be iron, Roman numeral 2, iron 2 nitrate. And just again to show you the math, here we have 2 nitrates each with a -1 charge to make a total negative charge of 2. And we have 1 iron that's supplying the +2 charge, so it must have a +2 charge itself. Calcium carbonate, back to a simpler one here. Calcium and the CO3 is carbonate, and calcium is group 2 metal, so we don't have to write a Roman numeral for it. And so, because we always know it has a +2 charge, and if you want to check out about what happened with the charges, you can say, well, carbonates come with a -2 charge. There's one of them at a charge of -2 to get a total -2 charge. Calciums come with a +2 charge. There's one of them, and that together makes that makes a +2 charge. So the +2 and the -2 make a 0 overall. Here we have aluminum. We said aluminum is a transition metal, but it's one of the weird ones. We always know it has +3 charge, so we don't need a Roman numeral on it. And we see SO4 and sulfate, you know, SO4 -2 has obviously a -2 charge. Okay, so we have 3 of the sulfates up there, and each of the sulfates has a -2 charge, so it's a total -6 charge for the negative part of this compound. And we have 2 aluminum atoms, 2 of them, and each of them has a +3 charge to supply a +6 charge for the positive part. So +6 and -6 equals 0, so this is a neutral compound the way it's written. Now I'm going to switch gears. We're giving you the name first, and now we have to write the chemical formula. This is going to involve a little math. Okay, ammonium, you need to know your polyatomic ions. This is one of the rare exceptions where the cation is not a metal. It's actually this formula, NH4, and the nitrate is NO3. Now I left off the charges, so I didn't really say the formulas for these polyatomic ions, but here's what they were. The ammonium had a +1 charge, the nitrate had a -1 charge. We do the crisscross rule to try to figure out and make sure that our charges cancel. You know that a +1 cancels a -1, but if you have to go through the crisscross rule, here's how you would do it. You would carry the absolute value of the charge on this ion down as a subscript to the other one, carry the absolute value of the charge on this one, carry it down as a subscript on the other one. And now you see they match and they cancel, so we would just leave it as NH4NO3. And again, you can see that we have a -1 canceling a +1, so the charge is overall 0. Here we have lead. We're told it's lead 2, so we know the charge on it. You would have to have memorized oxalate. It's C2O4 -2. We're not showing the charge yet. Here's the charge. Lead is lead 2 there, and oxalate is 2-. So when you bring down the charges, you see they again match each other, and you would cancel them like factoring in algebra. So our overall formula would be lead Pb C2O4, sorry. And you can see we had 1 oxalate with a -2 charge, 1 lead with a +2 charge, so the charges canceled out to 0. Now strontium bisulfate. Strontium, its symbol is Sr, sulfate is SO4, and bisulfate means it's got an acidic hydrogen on the SO4, so this is HSO4. The sulfate by itself would have been -2, but when you put an H+ on there, you get it, it comes down to -1. So the strontium has a +2 charge, the bisulfate has a -1 charge. We do our crisscross business, carrying the absolute values of the charges down and making them subscripts on the other partner. And we see, oh, they're not going to cancel out. So here's the overall equation, or formula for this compound. Sr parentheses HSO4 parentheses 2. We had to put parentheses around there for doubling something. We have to double everything in there. That's why we had to put the parentheses. So notice this time we knew the strontium had a +2 charge. It's a group 2 metal, so it always has a +2 charge. And we needed 2 bisulfates that each had a -1 charge to cancel that charge. So now to cancel the positive. So we got a +2 and a -2 to make 0. Tin 4 phosphate. I always like to say tin 4 is the trucker's favorite ion. Like tin 4, good buddy. Anyway, tin's symbol is SN, and phosphate's symbol is PO4. Phosphate has a -3 charge, and this tin, according to the name, has a +4 charge. And so when we do our crisscross business, we carry down the absolute values of the charges to the opposite partner's subscript area, and we see, oh, these aren't going to cancel out. So we got to write it like this: SN3 parenthesis PO4 parenthesis 4, because we had to quadruple everything in the whole phosphate, not just the oxygens. Okay, so again, this time we knew from the name, we knew that there was a +4 charge on the tin. And so 3 times +4 is +12. That's the positive part of the ion. And we have 4 phosphates, each one of them with a -3 charge. We've got a -12 overall. So -12 and +12 means that the total charge on the whole compound overall is 0. Mercury 1 oxide. Remember, mercury 1 is squirrely. It's an Hg2 that comes with a +2 charge. Oxide is oxygen in the ion form, and it's got a -2 charge, or a 2- charge. So doing the crisscross, you can see that we get to do some canceling, and we end up with Hg2O for the formula for mercury 1 oxide. You can see there were 2 positively 1 charged mercuries to make a +2, and there was 1 -2 charged oxide to make a -2, and the -2 and the +2 cancel each other to make 0. The neutral compound. Here's mercury 1 chloride. Again, the squirrely mercury 1 shows up as a pair of mercury 1s that have a +2 charge. And we got chloride. Well, chloride comes with a 1- charge. When we do our crisscross business to take the absolute value down, make it the subscript on the other partner in the compound, we can see that we're going to have to keep the 2 on the chloride. There's already a 2 on the mercury 1. So this is our formula for mercury 1 chloride. And there you have the math showing that the overall charge is 0. Just because it helps to memorize, to see patterns and so forth, I made this little table. You can see that it says, I've got this legend out to the right. It says out to the left. At right, the X's here represent either chlorine, bromine, or iodine. And these are represented in the name where we have these blanks as chlor, brom, or iode. So if I had IO2 - 1, I would have iodite ion. Or if I had BrO3 - 1, I would have bromate ion. Or if I had Cl - 1, I would have chloride ion. So you can just take the chlor, the brom, or the iode and put in the blank, and you will have the right name for the polyatomic ion. Here are a few examples. Hypochlorite ion, which just says it would have been XO with a -1 charge on the other page. Iodate ion, I with 3 oxygens and a -1 charge, and perbromate for the 4 oxygen version. Also have to talk about something else strange. You will almost always encounter oxygen as oxide, but every so often you'll find some weird versions. So when you have a pair of oxygens and they together make a -2 charge instead of a single making a -2 charge, then that's peroxide. And you'll have to look at the charge on the other ion in the compound to figure this out, that it's a peroxide, unless someone tells you the name. And hopefully it'll be an ion who's guaranteed to have just one form of charge, one amount of charge. So that's peroxide. Everybody knows H2O2 is hydrogen peroxide, right? So here's a weirder version of oxygen called superoxide, and it's a pair of oxygens making a -1 charge. So each one of them would be like having a half charge, half negative charge. In any case, that's called superoxide ion. It's very highly reactive, and it's not too common for you to run into it. Just wanted you to be aware in case you do. So if you need more instruction and or practice, you can go to Purdue's chemistry education website. Here's a link that you could try to reproduce in your URL. As you could take this URL and try to get it there into your browser. The chemical education resources at Purdue are very good, and they have a great section on, I think, even with some practice quizzes and so forth, where almost like flashcards or like a Quizlet that you can use. And I've also posted a video or two online on my YouTube channel, which is NPRET 2020, if you want to look up some of these, some other resources, video resources over naming.